Good morning, everybody. I'm Dr. Stephen Bartlett. I'm at the University of Utah Aida campus this morning, and I am a associate chair of the Department of Civil and Environmental Engineering. And I'm here to talk to you a little bit about our department and then maybe give you some things to think about. So the Department of Civil and Environmental Engineering has very many themes that it sees, and this introductory slide shows that we're involved with mobility and cyber-physical systems. These are predominantly transportation systems. We also are the keepers of the infrastructure, so we design and construct infrastructure such as buildings, roads, highways, bridges, ports, and those types of things. Also on the environmental side, we also strive to make the environmental interface with infrastructure much more sustainable. So the idea here is that the infrastructure should do no harm to the environment. And likewise, the environment needs to be compatible with the infrastructure. So this is kind of the various areas that we work on. And mainly in civil and environmental engineering, we're trained to be designers. We also are associated with construction and operation, predominantly of infrastructure. So just to introduce myself, some of the things I've done. Of course, I've studied a lot for many years to get a doctorate degree. I'm also a licensed professional engineer in the state of Utah. I have been so for about 25 years. I also am a geologist. I have a bachelor's degree in geologist. And right now I'm trying to become an amateur musician. I'm not very good at it, but I'm working on it. A couple of the things that I've done and I'm currently working on, right now I'm working on the George Lucas Museum of Narrative Arts in Los Angeles. We're currently looking at how to essentially do the Green Garden roof that you see on top of this structure. And so there's a lot of design considerations that have to go on. And I'm helping the design team work through those and get the design permitted with the city of Los Angeles. Another thing I did earlier in my career was I was one of the designers for the interstate through Salt Lake City preceding the 2002 Olympics. I worked for the Department of Energy for 5 years at the Savannah River site, mainly working with hazardous and radioactive waste and how to dispose of it properly. I was also a consultant to Disney for Disney Shanghai and helped with some of the terracing and things that you see around this and some of the issues associated with how to build these terraces and plazas without causing settlement. I also been involved in the light rail system and design of some of it in Salt Lake City. This case here is kind of a novel case that you see on the right is an embankment being built out of polystyrene, which to you would be styrofoam. So it's quite a novel construction that went on some about 10 years ago. I'm also an earthquake engineer. Spent much of my career looking at what earthquakes do in terms of damage. On the left, I visited Taiwan in 1999 during the 1999 Chichi earthquake and looked at this diversion dam that was badly damaged by the earthquake. I also did a lot of my dissertation work looking at earthquake damage. And this photo on the right is a photo of the Alaska earthquake during 1964 and some of the bridge collapse that happened. I've also been involved quite heavily in my career in the disposal of hazardous and radioactive waste and radioactive waste facilities. So let's spend just a minute thinking about questioning. When you come to university, you'll find one of the things that we do is we ask students a lot of questions. And we expect students to respond to our questions. And so this quote from Einstein, I think, shows us the importance of learning how to ask the right questions. He said, if I have an hour to solve a problem and my life depended on the solution, I would spend the first 55 minutes determining the proper question to ask. For once I know the proper question, I can solve the problem in less than 5 minutes. So particularly in our introductory classes, that's what I do. I ask you a lot of questions about things, and it's for discussion about some of these questions. There may not be any complete solutions that society or engineers currently have. but it's important for us to understand that by questioning, we can arrive at some very important solutions. So what we need to do in engineering is have a very rigorous logic thought. And it kind of goes like this. We ask questions that lead to formulating potential answers to those questions. When we start formulating ideas, that might generate potential solutions. We test those solutions, sometimes just numerically, sometimes experimentally, sometimes actually in field tests to see if they might work. And then we may have a concept that could be implemented and brought out into the public domain. So this is what we are. We're fundamentally problem solvers. We take societal issues and we try to find solutions to them. So right questioning leads to the ability to create solutions, make decisions, and formulate plans. And that's what we need in a formal decision-making process. So today we're going to see if we can start asking some questions about climate change, a very important topic because climate change is affecting the globe. It is also affecting many cities and urban areas in many ways that will be irreversible. And so we have to plan for this and how we are going to respond to this over the next 15 or 20 years. I would put forth to you that climate change is the largest issue of your generation, the one that you will have to deal with in many, many different ways and come up with innovative ways to mitigate its impacts and solve some of these problems. So I have Mentimeter here. Let's see if I can bring that up. I have a set of questions I'd like you to answer. So let me give you some instructions how to do this. You should see on the screen a link to go to menti.com. And when you get to menti.com, it will ask you for an access code 912931. Again, that's 912931. And this first question is to rank what you think are the most important questions in terms of climate change. So these are shown first, second, third, or fourth, but that doesn't necessarily mean that's the correct rank. So according to you, what is the most important question? Rank that first, then the next important is second, and so on and so forth, the third and fourth. Okay, so I'll give you just a few minutes to respond to that. And we should be able to, if everything's working, watch you as you vote on these. These should appear on the screen.
It's showing your screen share, but I'm sending a message into the chat with the link and then the code.
Okay, let me try something here.
It just shows your.
How about now?
Yeah.
Sorry, my fault. Here we go. Now we're starting to get some rankings. So wait just a minute later. So make sure that you get there. Menti.com 912931. Okay, looks like we've had 3 respondents so far. Four. I think we have a couple others out there if you wouldn't mind voting. 5. Okay, go ahead and keep voting, but I think it's not going to change the results too much. So since I have one of our students here that's a civil and environmental engineering student, Daniel, I'm going to ask you a question here too. So don't feel bad. Think about this. What is your opinion about climate change? Is it really occurring?
Yes, I think it's really occurring.
I agree with Daniel. There's much scientific evidence that shows that climate change is occurring. So I think it's really a question that maybe it was important 10 years ago, 15 years ago, but is no longer that important to us. I think that's been proven. What is climate change doing to the environment? Now that, what's your opinion about that one, Dan?
It's impacting the ecosystem and the society we live on.
So this is one we're still trying to understand, I think. But what is climate change doing to the environment? We see rapid changes in ecosystems throughout the world. And so this one is, I think, a very important topic. What can we do as society to affect climate change? I won't make you answer that one, Daniel, but it's clear, I think, as is probably as important as the environmental change because it's affecting societies. So question number 2, with rank number 2, deals with the environment. Number 3 really deals with societies. And this is where civil engineers and environmental engineers really come in, is what is the climate change doing to the environment and how does that change in the environment affect the societies and what does society have to do to react to that? So some of it might be mitigating the effects of climate change. Some of it may be just adapting or being resilient to the changes. Okay, what can we do to slow climate change is a very individual and important question that you need to ask yourselves. And so that's an individual question. I think it is an important question, and it's one that I challenge you in my courses to think about. How can you individually contribute to reducing the effects of climate change? Okay, well, thank you for your participation. Let's see what we have next. I think I'll close this for now. And I believe you should now see my PowerPoint again. So if you don't, let me know. This one I'm not going to go into Mentimeter, but I think you need to ask yourselves, are you greatly alarmed by the rate of climate change? Scientists are sending out a strong warning to us, a united warning to us, and warning us about what they are seeing. There's a fairly united front about this. And I think it's a general consensus that the consequences of climate change will not be minimal. I'm not going to use the word catastrophic, but they will be very challenging. And what I want to instill into you is the idea that we can make changes and adapt. We have to. We have no other choice. And so this is where I think I would like, most of you in this next generation to think about what are some of the creative things you can do to respond to climate change and help societies adapt and become more responsive or more resilient. So solving this problem takes a community. We as practicing engineers are always seeking solutions compatible not only with the environment, but what are the community needs. So it means a lot of interaction, going out to public meetings, public hearings, and taking public input. So this is all important because, if we want to go fast, if you want to go fast, go alone. But if you want to go far, you have to go with others. Okay, you have to go together. So we are guardians of the infrastructure. This is just to remind you that almost everything you do involves civil and environmental engineering, from the buildings you live in, to the roads you drive, to the transportation systems you take, to the water, wastewater treatment systems that you use. The traffic systems are all designed by some branch of civil and environmental engineering. Okay, let's turn our attention just briefly to climate change and some of its impacts. So this slide lists some of the major impacts and not all of them. and it's focused, as you can tell, on infrastructure. So in the center, you see the infrastructure I just mentioned, the roads, the highways, the power lines, all of those things. And we see that these external factors that are working on them, including flooding and erosion, high temperature extremes bringing mainly increase in wildfires, other things like heavier rainfall, which can cause flooding, landsliding, stronger winds, as we'll learn at the end of this lecture, which can damage not only high-rise buildings, but transmission lines and other forms of infrastructure. So just to give you an idea, in the United States, there was a catastrophic hurricane that hit New Orleans. It's called Hurricane Katrina. And unfortunately, what it did is it caused a surge in the sea level and a rise that compromised the city's protective levees. New Orleans is below sea level. It's subsiding with time. It's going down. And so the city is now, some places as much as almost 3 meters below sea level. So those protective levees help things from getting flooded. Here's down in this lower left-hand corner, you can see a levee, and it has been broken or breached, and it's now allowing waters to enter into the city. Now there's a temporary try to fix this, but unfortunately the city was mostly flooded, and large residences, as you see here, were flooded. So these homes all were abandoned. Some may have been able to be remodeled, but refixed, but for the most part, many were abandoned. Okay, so one of the things that we're going to see is increased flooding and erosion. The increased flooding probably comes from two factors: a rise in sea level and also increase in storm intensity. So storms will get larger. Hurricanes probably may get larger. And then, of course, the erosion comes from the flooding itself. As things flood, then we can see not only damage to levees, but roadways and other things that are exposed to them. Okay, another thing that climate change is going to present to us is higher temperatures and higher temperature extremes. So I guess, if you like air conditioning, you probably can still continue to sell air conditioning. Do a little bit of air conditioning surfing here, as we see in this cartoon. But as you can see on this picture in the upper right, there is a prediction of much higher temperatures throughout most of the globe. This will cause drought, failing of crops, and also in areas that are more natural, the drying out of plants, trees, which lead to wildfire. And the many wildfires that we saw in Australia this last fall, winter, were a result of probably increasing extreme temperatures and drought. And so this map just shows you all of those were fires that were actively burning in Australia. So let's watch just a brief video about this. Hopefully the audio works. Let me know if it does not. So, brush fires, probably very important here in Korea because of the vegetation that we have. Very important, particularly in the western United States too. There have been large fires in California, done damage of many, many homes as the fires came down into residential areas. Now, another thing that you may be less familiar about is heavier rains also increase the amount of water that's in the soil. And a lot of the soil might be on steepened slopes, and as the water infiltrates into the soil, it can cause a failure and cause what's called a mudslide. So I'm going to show you some fairly graphic video from São Paulo, Brazil, from a recent mudslide that occurred right in the city boundaries. So keep watching kind of up in this area right here, and you'll see the mudslide. Okay, so obviously this is a great hazard. Mudslides have killed several hundreds of people. And so particularly when we have two factors going on now. We have sometimes wildfires that come and remove the vegetation. And then we have rainfall that comes, and when it falls on the ground now, since there's no vegetation, there's not as much capacity to absorb that water. So it gets into the soil becomes heavier, it gains in mass, and if it's on a steep slope, it can just flow. It literally can almost turn like to a river of mud, and that's why it's sometimes called mudslide. And when it gets in flowing out, sometimes it combines with rivers and streams and turns into what we call debris flows. And so these are catastrophic and very dangerous things. Okay, so we're going to talk a little bit about wind next, and just to kind of keep this a little bit light. What happens when an engineer designs a scarecrow? Well, I don't know if everybody knows what scarecrows are. So I've given you some pictures here. These are placed in the fields so that when the birds come in to eat the crops, they're supposed to look like men. And so the scarecrows don't, the crows and the birds don't dare land. Okay, so they're to scare the birds away. Okay, so I want to give you what happens when an engineer designs a scarecrow. Well, is it ugly? I don't know. These are not designed by engineers, by the way. Can it fly? I don't know. Nothing. Engineers do not design scarecrows. Well, let's take a look. Okay, well, that's kind of interesting. Actually, this is harder than you think to make something do like this, because there has to be something down here that allows that rod to pivot both this way and go back and forth this way. So there's a little bit of really mechanical engineering going on here. Of course, this is a rod with some bicycle handlers, and now the scarecrow itself has to catch the wind like a kite. And it has to be able to also move up and down too. So I thought that was kind of an interesting use of engineering, by the way. So let's talk about stronger winds and hurricanes. Here in the far east, they're called typhoons. But in the Atlantic coast of the US, they're called hurricanes. And so they're the same phenomenon. It's just depending on where you're at. But these are massive storms that not only bring high winds, but also bring heavy rainfall. We had a very severe case of a Category 5 Hurricane Dorian hit the Bahamas and essentially stay stationary over the Bahamas for almost 2 days. with extremely high winds. And it caused massive damage, particularly to things that are not anchored down. This appears to be a trailer, so you can see the wheels. And the wind was strong enough just to flip it over. And that's not really that surprising because these are fairly lightweight buildings. But there was massive damage. Also, what happens during hurricanes is because there's a depression, meaning essentially that there's a decrease in the barometric pressure, the water levels come up. So this is the storm surge that could come in addition to the high tides, can be very devastating to lowlands. So let's just take a look at what some of the winds may have looked like. This is coming from the Bahamas during the peak of Hurricane Dorian. Now, I've been in the Bahamas twice, and most of these higher, taller palms that you would see would have already many palm leaves on them. And see, they're just completely stripped off. It's just gone. And you notice these lower palms are, they're a little bit stronger, but they're being challenged. So this type of damage can damage communities so severely that it takes decades to recover. New Orleans is still recovering from Hurricane Katrina. Some of the people that are displaced, tens of thousands of people left the city and never returned, never came back. So in terms of typhoon and wind action, I think this is what I want to spend a little more time with because I have a couple experiments to maybe show you what we would do in terms of designing infrastructure for high winds. And this next video is from an American Society of Civil Engineers video feature presentation called Dream Big.
Apparently with the Australian wildfire video, the audio wasn't working. Someone messaged me about it. So I don't know if this has audio on that one.
It wasn't very strong, but let me try it. Oops. It's the subtitle. Okay, so let's pause there for a minute. I need I'm going to stop the screen sharing and turn the camera on me. Let's see. All right, where is the controller? There it is. So let's see if we can zoom on, on me a little bit here. There I am. Right there somewhere. Okay, I have a structural frame here. I'm going to speak really loudly, so hopefully everybody can hear me. Can you hear me okay? Hopefully so. Maybe I can do it from this side. So you can see the structural frame right here. And at the top, there's some weight. And this is essentially a series of columns and floor. And it gives this structure some stiffness. It's fairly strong in this direction as I try to twist it, but it's more flexible in this direction. Okay, so if the wind comes in and hits against this building, it can shake it. So to kind of replicate the wind, I have a piston here that pumps back and forth. Still on camera. I can't tell if I'm within the screen or not. I'll stay right here. So the piston pumps it back and forth. So the idea is I'm going to make this structure go back and forth and see if there's some types of speed or frequency which this structure starts to respond. We use the word resonate. So everything kind of has its own frequency of vibration, even buildings. And if something's pushing against them, if it's doing it at the right frequency, then the building actually starts to resonate or respond to that. If it's at a higher frequency, it may not. And I'm going to show you at least two ways that this building can vibrate. One very damaging and one very unnerving, but not so damaging. Okay, so let's first look at the damaging one. So I'm going to turn on my power supply. And with my wave generator, I can change the pulsing back and forth from 1 hertz all the way to 100 hertz. 1 hertz is 1 cycle per second. 1 second. 1 second. 100 hertz is I'd have to do that 100 times in 1 second. My arm's not that fast. So I'm going to turn this down to 1 hertz. Now I also have a dial here that I can control the amplitude. That means how far out does it push. So I will just start this pushing back and forth, get everything in line. This also pushes and it has a rubber band in so it can pull back too. And 1 cycle per second, we see a little vibration in this, but it's really not too dramatic. In fact, I guess I could get really fancy and hook up my accelerometers. I forgot to do this when the lecture started, but give me a minute to bring up the accelerometer, and we can measure the accelerations here at the roof line. So this is software that communicates with the accelerometers. And the accelerometer is this little black box sitting up here on top. And the accelerometer can measure accelerations in this direction, and this direction. So it's 3 component. So as you're looking at this, the Z is the up and down, Y-axis is this way, and the X-axis is this way.
Make sure you start screen sharing.
Oh. I got to start screen sharing, sorry. I'm glad we have people to keep us straight in this room. I haven't tried all this multimedia stuff. So I will screen share this. Now you should be able to see the accelerometer. Let me enlarge this a little bit. Okay, so the blue is up and down. The yellow is back and forth this way, and the green's back and forth this way. For some reason now, when I go into screen share, it quit recording. Oh, okay, just paused. All right, so you see some, so you know, it's like, if I shake this a little more, you can see what happens. Okay, that was an earthquake, by the way. That's what earthquakes do. Okay, so it's taking a minute to recover back, to kind of get back to the original scale. I kind of messed it up for a minute. All right, so you can kind of judge a little bit about how much this is shaking it. I think even if you watch me closely, you should be able to see this frame start going back and forth. So 1 hertz is not really doing much, so I'm going to just kind of start moving this up. You in the room can probably hear it clicking a little faster. So everyone here now, the top of this building shaking a lot. Okay. So if you were in these top stories of this high rise, you would be being flung around the room, trust me. And it could be very unnerving to you and very damaging. Also, if the motion's strong enough, like we might see in an earthquake instead of wind, it could begin to damage these columns. And then there could be potential building collapse if the building's not strong. Okay. This is called the fundamental mode of vibration. This is the most damaging because what it's doing is getting the largest displacement back and forth, back and forth. And that's what does the most damage to the column. But that's not the only way that structures vibrate. They have multiple ways they can vibrate, particularly the long, slender structures. They can vibrate in the fundamental mode. They can do other more advanced modes, or sometimes they can even excite a torsional mode. That's why that twist that he was talking about helped, because the wind tried to go around the building. Its aerodynamics changed, and it reduced the forces on the building. So it reduced the, the potential to do damage. All right, so we've seen the fundamental mode. I think you kind of get an idea, but this is another more funky mode. Let me see if I can get there. Now we're going faster. Now right now, there's a little bit of vibration in here, but it's standing pretty still. So this frequency, I'm at 5.7 hertz, almost 6 cycles per second. It's not doing much. You can see if winds were exciting something like that frequency, we probably wouldn't be that concerned about it. But let's keep going. Now this is really cool. Because the top is really not vibrating much. But look at the middle. It's going crazy. This is what we call the second mode of vibration. And we're cycling at almost 9 cycles per second. So now you can see this would be doing a lot of damage in the middle of this structure. If you were on these floors, yeah, you would be really, really concerned. So part of design, particularly of high-rise building, is understanding these modes and how do they occur. So it's part of what we call structural dynamics. And it's now all of our accelerometers are going nuts. Even up here on the roof, we're still shaking. But if I put the accelerometers here, we find out the amplitude would even be higher. You can see that with your eye. So what we have to do is anticipate what will be the modes of vibration of the buildings. Now, this is not something easily done experimentally because, you know, if I took over I live in the 22-story high guest house over here, and there's really just no way I can attach something big enough to try to shake it. And even if I did, nobody would want me to do it because I damage the building. So a lot of this has to be done through advanced computing modeling. And so what really controls how this building vibrates is how tall is it, how slender is it, and how stiff these columns are. The stiffer they are, the less flexible it is, but the looser we make these, or the less stiff we make these, then the more flexible it becomes. And so the building flexibility is greatly controlled by this building. Now, we get into advanced buildings, there's all kinds of internal bracings and frames and skins that make this, challenging. So this is advanced computing, supercomputing type of things sometimes are used to model these. Okay, so I think it's time maybe to just kind of wrap up. What I like about civil and environmental engineering, remember I was trained as a scientist. I'm fundamentally a geologist. But what I like about civil environmental engineering is because it allows me to apply my science, I think, to many, many different types of infrastructure. And oh, by the way, it doesn't pay badly either. For example, engineers at my level with 25 to 30 years experience in the United States are making quite commonly $150,000 to $200,000 a year. So it's a very rewarding profession. Even with bachelor's degrees in the United States, now you're getting $60,000 to $70,000 starting salaries. By the time you're maybe 5 to 10 years in, that could be going over $100,000. So, and there's a shortage of engineers. Well, I guess we're scaring too many people away with our math and science. I don't know what it is, but we do have a fairly rigorous curriculum. But what we now be able to do is take the principles of science, the principles of mathematics, and try to use that knowledge to overcome some of these things. I have great hope that this next generation will meet the challenges of global climate change. But we're only going to do it through communication and talking to one another and coming up with solutions that meet the greater good of the community. We're going to have to probably continue to get better at some things in terms of energy use, preservation, and how we use materials like plastics and others, and how we sometimes misuse them. And we're just really going to have to be a lot smarter about how we start generating energy. Okay? So those are some of your challenges. As we continue to build these urban infrastructures that we live in, it's going to be a continual challenge to be stopping not only climate change, but preserving our precious resources that they can go on for other generations. Unfortunately, my generation maybe wasted too much time on this. The crisis was creeping up on us, but we tended to ignore it because it wasn't affecting us directly. Now it is. So I'm going to open up now for questions. I don't know how, I guess they could ask us remotely too?
Yeah.
So are you following the chat?
Yeah, I have it.
Okay, so anybody in our audience of 4 have any questions?
After graduate the civil and environmental, what kinds of careers that we?
Oh, that's a good question. So civil engineering is broad. So civil and environmental engineering. Let me just list some of the types of things that they do. So many go into transportation engineering. I'm a geotechnical engineer, so that means I design things where infrastructure has to interface with earth, mainly rock and soil and water. Okay. There are structural engineers that design buildings and frames like that. There are water resource engineers that deal with delivering clean water systems and also deal with wastewater and stormwater systems too. You may not know what stormwater is, but anytime we have rain, we have to take that water off the roads and take it somewhere. Also, water resource engineers predominantly in the past have been also dealing with dams, hydrological dams, things like that. And in terms of, see if I'm forgetting anybody, environmental engineers and biological engineers, they are mainly working with how initially they did 20 or 30 years ago, how to help deliver clean water. But now bioengineering and environmental engineering is probably one of the leading groups of civil engineering leading in terms of sustainability. And sustainability is this general broad concept of how can we live in a sustainable manner so that we can pass on the resources, the energy to our future generations without continuing to degrade the environment. Okay. So environmental engineering is very much at the forefront. Maybe even a third of the engineers now are going into environmental engineering. Also, environmental engineers, when I was working, were dealing with how to keep pollutants from getting into the groundwater, solid waste, and hazardous waste management. So these are areas. So those are some of the fundamental disciplines of civil engineering, but civil engineering is changing and adapting. We're getting into big data, sensors, smart cities, autonomous vehicles. All these things are topics within, we're at least contributing to in civil engineering. Then some of our graduates go out and go into law. We've even had a few go into medical school through our route. So there are public service planning is also somewhat associated with civil engineering. We have a lot of interfacing with architecture too, particularly in buildings and infrastructure, urban infrastructure. Is that it? Is that a good answer? Okay. Nobody else wants to know?
Here, I can give one.
Okay.
So say someone doesn't know if they technically want to go into engineering, but they know that they generally want to go into a STEM field. What class, or do you think, what sort of curriculum should they take?
Well, my advice is to take the introductory courses in both. So if you don't, and we only have really one science degree and one engineering degree, which has science in it. So urban ecology would be the science aspects, and it's, kind of working on the science side of the environmental concerns and issues, where engineering is working probably on the applied side. So I would take introductory courses in both. We offer a course in Civil Engineering 1000, which talks about urbanization, congestion, climate change, sustainability, some of those broader topics, and infrastructure. And likewise, I think urban ecology has, a similar type of class. So you take that and just see what's best for you. Frankly, to me, I think it's just a little bit of kind of your first, maybe a semester or two, maybe not completely committing to a program and trying them both out would be my advice. Nothing in the chat. Well, good. You're welcome to see us. I think we can be found on the website, both here on the Asian campus. You should be able to find our curriculum. I'm not going to talk too much about our coursework and curriculum, but it is a 4-year program where you also spend 1 year in Salt Lake City. So it's a chance to learn more about these topics. And as juniors, you take core courses in transportation, water, geotechnical, structural, materials, and all of those, okay? So you get a chance in Salt Lake to see the broader breadth of civil engineering. Here we will have 3 to 4 faculty that will be teaching, mainly freshman, sophomore, and senior courses. Thank you. Goodbye.